Assalamualaikum and hi. So this is experiment 3 report for minor losses in pipes by group 1.
This is our group member, Lim Zihui, myself, Nurainun Bashira, Nurul Afifah, and Afid Daniel.
This is our table of content.
So for introduction, designing effective system including water supply networks and industrial pipelines requires an understanding of fluid flow through pipes, which is a key component to fluid mechanics. Minor losses brought on by fittings, bands, valves, and variation in pipes diameter can also have a very big impact on system performance, even though major losses from friction are well studied. Through the measurement of pressure drops across various pipe parts and configuration, this experiment explored these small losses. Examining the effects of these losses on the pipeline system overall energy efficient is the aim. The experiment offers important insights for pipe designs, optimization, and enhancing fluid transport system in real-world application by investigating the link between flow velocity, pipe shape, and pressure drop. Therefore, the objective of this experiment is to determine the loss coefficient KL value and minor head loss HLM in pipe components or fittings for different water flow rates, pipe diameters, and pipe bands.
The flow in the piping system at different flow rate may be required to pass through a variety of fittings, bands, or rough change in area. Additional head loss called minor head loss are encountered primarily as a result of flow separation. By simplifying the Bernoulli equation between 2 points of the horizontal Z1 and Z2 pipe, the pressure loss and the total head loss could be determined as follows. So equation 1 is the Bernoulli equation, and due to there is no Z1 is equals to Z2, so we simplify it. And then the equation 2 is the equation for the total losses, total head loss, and equation 3 is the head loss, and then equation 4 is the minor loss, and then equation 5 is the equation used to calculate the total loss, which is we combine equation 3 and 4, and we get equation 5. So it depends on the equation. When we look at the equation 4, actually the value of minor losses is strongly depend on the value of KL. And how do we determine the value of KL is actually strongly dependent on the geometry of the component. So in many practical applications, so the RE is large enough so that the flow through the component is dominated by initial effects, and leaving the viscous effect as secondary importance in a flow which is dominated by initial effects. It is usually found that the pressure drop and head loss correlate directly with the dynamic pressure. Therefore, the friction factors for very large RE in fully developed pipe flow is independent of the RE. The same condition is found to be true for flow through pipe component. Thus, in most practical cases, the KL for components are a function of geometry only. In this experiment, the KL value and HRM in pipes for different water flow rate, pipe diameters, and pipe band will be determined. So the description related to each of the test geometrical as follows. So the part 1 showing the sudden expansion and sudden contraction KL. And then you can refer to the figure 1. So the value of KL for the fluid flows sudden enlargement and contraction can be obtained by considering by continuity equation 7, momentum equation 8, and energy equation between point 1 and 2. So here are the resulting equation 7, 8, and 9. So basically, if we want to calculate the theoretical KL for sudden expansion and enlargement, we are going to use equation 9 and 10. So for the second part, we have elbow, pipe bands, and pipe branch. So for the figure 2, we can actually directly refer to the figure 2 to determine the typical value for KL for pipe components. What we use in this experiment is 90-degree band, 90-degree angle elbow, and then also 45-degree, and then also T-type and Y-type branch. So we can determine using this diagram.
For the experiment setup, we have inlet valve, main switch, manometer tube, connected tube, and outlet valve. At the manometer tube, we have determined the H1 and H2, and then for the pipe selection, we have highlight the part of the sudden enlargement, sudden contraction, Y-type, T-type, angle 90 degree, band 90 degree, and angle 45 degree. For methodology, the first one, the main switch and pump were turned on. Then valve V1 and V11 were fully opened in the pipe section for sudden enlargement and sudden contraction. And then the control valve was slowly opened, turned counterclockwise to the maximum position, and for a while wait to remove any bubbles in the flowing pipe. Then the inlet flowing pressure H1 and outlet flowing pressure H2 were identified, and the manometer tube was connected. And the volume of H1 and H2 in millimeter at the water manometers inlet and outlet were recorded. Step 6. The knife valve was closed to collect 3 liters of water collected in the tank, and the time needed to measure the water flow rate Q were recorded. Step 7. 5 different flow rate Q were determined by reducing the opening of the outlet valve, which is V11. Step 8. Once finished, the manometer tube was removed first to avoid the bubbles in the tube, and then the inlet that related valve for next pipe was opened, and any valve not related to the water flow was closed. Next, step 4 to 8 were repeated with the various tested components in the pipe section as shown in the figure 3. For Y-type, we use the V3, V8, V10, and V11. For the T-type, V3, V7, V10, and V11. And then for the angle 90 degree, bend 90 degree, and angle 45 degree, we use the V5 and V11. Once all the tasks were completed, all connected tubes were removed from the system and the control valve was fully opened, and lastly, the pump and the main switch were switched off. Here the result for the experiment minor losses in pipe, which is for figure 4 shown that the data for sudden enlargement and sudden contraction, and figure 5 shown that the data for elbow and pipe bands. The next result is shown in the figure 6, which is for the data for pipe branch.
For the discussion part 1, we have calculate the minor head loss and KL value for each of the pipe component. So before we start, we need to determine the viscosity first by using the temperature equals to 36 because we want to use the viscosity to calculate our Reynolds number in this experiment. For this page is the general calculation for the internal diameter and also the cross-sectional area for the pipe for sudden enlargement and also sudden contraction, and also the loss coefficient KL value for the theoretical KL for using the formula listed in the diagram, also figure 7 and 8, and also the kinematic viscosity. So in this case, the kinematic viscosity, just like a previous page, is still the same. It's 7.516 because the temperature is constant. So in this table 1, it shows the data for sudden enlargement. So I have recorded this table consists of all the value of experiment and also the theoretical value that we have calculated. So we have Q, H1, H2, and then the differential pressure, and then also the velocity, and so also the Reynolds number, friction factor, and also the total head loss, and also the minor head loss and major head loss, and also the KL value for theoretical and experimental. So we can observe that the velocity value is larger than velocity value at 2 because at the velocity point 2 experiment enlargement, so the area become larger. Of course, the velocity is decreasing, and the value of H1 is always lower than value of H2. And because the pressure in point 1 is lower than point 2, as velocity in point 1 is higher than velocity at point 2. And all the flow rate in this experiment is turbulent flow. And the friction factors, we can see a phenomenon when it is increased when the Q is decreasing. And also for the last two columns, we are calculating the KL value for the experimental, and the theoretical, we're using the formula. For table 2, there are percentage error for the theoretical and experimental. So the highest percentage error is 26.7 and the lowest is 9.14. In table 3, we can observe that the V1 value velocity is always lower than the velocity 2 because the point 2 experience contraction, so the area becomes smaller and the velocity increase. So the H1 value is always higher than H1 than H2, and because the point 1 pressure is higher than the point 2. And same goes to this sudden contraction. It undergoes the turbulent flow as the Reynolds number is more than 3,000. And then the friction factors also increase when the Q is decreasing. The last two columns is the value of, we calculate the experimental KL and also the experimental KL value for theoretical. For the table 4, the percentage error for sudden contraction is quite high compared to sudden enlargement. The highest is 33.46 and the lowest is 4.85%. This page shows the general calculation for the 90-degree angle, 45-degree angle, and also 90-degree bend pipe. So we in this figure 9, 10, and 11, we actually calculate also the general internal diameter and also the area and also the KL value we determine by using figure 2 and also the kinematic viscosity. Table 5 shows all the calculations for the angle 90-degree, bend 90-degree, and also angle 45. So for the 90-degree angle, 45 angle, and also 90-degree bend, so we can see that the value of H1 is always higher than value of H2. This trend is because where there is minor losses, there is a bend, and the angle will cause actually pressure drop in the pipeline. So the theory is proven as the value at the point 2 is very low compared to H1. So all flow rate is still turbulent flow, and also the friction factors is increasing when the flow rate is decreased. So we are last two columns, we're going to determine the KL value. And also the percentage error. So for the percentage error, we get a quite low percentage error in this case for the 90-degree angle. The highest is 7.89 and the lowest is 1.29. In table 7 showing the percentage error for the 90-degree band. So the 90-degree band overall is quite high as the theoretical KL value is supposed to be 0.4, but we actually get around the range of like 0.58 to 0.48 for the lowest KL experimental value. So the highest percentage error is 46.97 and the lowest percentage error is 22. In table 8 shows the percentage error between the KL value for 45-degree angle. So the percentage error is also quite low, and the percentage error is 1.3 with the lowest and 9.4 is the highest. And then the KL theoretical is 0.8 and the KL for experimental, the range is between 0.76 until 0.87. In the figure 12 and 13, also showing the Y-type and T-type calculation for the internal diameter, cross-sectional area, and the KL theoretical value, and also the kinematic viscosity, and also the gravity constant. Table 9 shows the data for the Y-type and T-type, and we can see that the H1 also are always higher than H2 because the pressure drop. For the KL value percentage error for Y-type, so we can see that the overall is quite low. The lowest percentage is 0.36 and the highest is 2.5. And the KL value for the T-type, the percentage error is around, the lowest is 2.7 and the highest is 14.39.
For the next discussion, we discuss about the effect of the different water flow rates, pipe diameter, and pipe bands on the value of loss coefficient. The value of the loss coefficient K depends on the factors such as water flow rate, pipe diameter, and the type of bands in the pipe. At higher flow rate, the implicit value of water creates turbulence, causing more energy loss and rising the loss coefficient value. In contrast, at lower flow rate, the flow remains smoother, which is laminar, which result in smaller losses and a lower loss coefficient. And then, narrow pipe lead to faster water flow and higher friction, increasing the energy losses and thus the loss coefficient value. In contrast, wider pipe allow water to flow with less resistance, reducing the loss coefficient. Lastly, pipe band greatly influence the loss coefficient. Sharp band like 90-degree turn disturb the flow more significantly, leading to the greater energy losses and higher loss coefficient value. On the other hand, 45-degree allow the water to transition more smoothly, minimizing turbulence and reducing the loss coefficient. Understanding this relationship helps in designing efficient piping system with minimal energy losses.
For increasing experimental data and the possible recommendation to improve the existing results. First, air bubbles in pipes, so we properly ensure there is no air bubbles flow in the pipe by flowing water into the pipe and securing every connection properly. Next, parallax error. Make sure the eye is perpendicular to the meniscus level and take several readings to get an average reading. Next is the preparation of water reading in a manometer. Ensure correct calibration and a stable fluid to avoid fluctuation.
Here are some of the safety procedures should be conducted during the experiment. Number 1, which is we should handle water carefully to avoid spills and slipping hazards. Number 2, we should wear appropriate personal protective equipment, PPE, such as lab coats, gloves, and closed-toe shoes. And lastly, we have to make sure the eye is perpendicular to the reading of the manometer to get accurate reading and avoid parallax error.
So in conclusion, for each diameter, water flow rate, pipe bands, and pipe diameter each have its own different loss coefficient and minor head loss. The findings demonstrate that fitting geometry affect loss coefficient with larger losses occurring from acute bands and diameter changes. Smaller diameter result in larger losses while minor head losses rose with flow velocity. The correctness of numerical formula was confirmed by a close match between experimental data and the theoretical expectations. All things considered, the experiment used below crucial pipe shape, flow rates, and fitting types are to reducing energy losses and maximizing fluid transport efficiency.
This is our reference. This is our reference. This is the link for calculation. This is the link for calculation. Thank you. Thank you.